Hi hello namaskara, welcome to Tech Girl Kannada YouTube channel.
Here the questions are like compare the order of growth of half n into n minus 1 by n square. We'll keep the constant half left side and limit n tends to infinity of n square minus n by n square 1 minus n 1 by n then equals to half, which is a positive constant. Functions have the same order for all the growth, which is constant. Then compare the order of growth of log to the base 2n by root n. Log 2e 1 by n. It can be written as like this. Then root n can also be taken as half root n. Why? Because we have done the differentiation of numerator and the denominator. So we will have root n by n that is equal to 0 and tends to infinity by 0. Log n to the base 2 has a smaller order of growth than root n. 0. If the answer is 0, then this has a smaller order of growth than root n. Compare the order of growth of n factorial to 2 power n. N factorial is root 2 pi n by e whole bar n. Under the denominator is 2 power n. The differentiation of n factorial is root of 2 pi n by e whole power n. Then 2 power e power n by 2e whole power n. That gives you the infinity. Then 2 power n grows very fast. N factorial grows still faster. Therefore, n factorial belongs to big omega of 2 power n. So for the first one, we have used theta of n square because it is constant. Since the answer came as 0 equal to 0, then it is smaller growth value. So that is big O of n. Larger growth value or faster, it is omega of 2 power n. Unlike big O, little o, rarely used in analysis of algorithms. Mathematical analysis of non-recursive and recursive algorithms with example. Mathematical analysis of non-recursive algorithms. Finding the value of the largest element in a list. For max element of a list, max value equals to a of 0. For I 1 to n minus 1 do if a of I is greater than max value equal to a of I, then at the end return max value. Number of comparisons will be same for all size. So it is distinguished as C of n equals to 1. Sigma I to 1 n minus 1, 1. So that gives you algorithm makes one comparison on each execution. So upper bound minus lower bound plus 1. One comparison. So that's why we use plus 1. So upper bound minus lower bound is n minus 1 minus 1 plus 1, which will be n minus 1, that is equal to theta of n. Element uniqueness problem. Check whether the all elements in the given array are distinct. For I 0 to n minus 2 and j I to I plus 1 to n minus 1 do If a of I equal to a of j, return false or else return true. Number of element comparisons will depend not only on n but also whether there are equal element in the array or not. So that is why I equals to 0 to n minus 2, j equals to I plus 1 to n minus 1. Then we have I equals to 0 to n minus 2, n minus 1 minus I plus 1 plus 1, that is equal to n minus 1 minus I. Then instead of I, we use this upper bound minus lower bound. I 0 to n minus 2, n minus 1 minus I equals to 0 n minus 2. Where we will get n minus 2 minus 0 plus 1. Then for this minus we have n minus 2 into n minus 3 by 2. Why that has become n minus 3? Because that is nothing but n minus 2 to I plus 1. I plus 1 to n minus 1. So that is why we have I will be equal to n minus 2 into n minus 3 by 2. 2 of n minus 1 into n minus 1 minus n minus 2, that is n square minus 2n plus 3n minus 6, that gives you n square plus n minus 4 by 2, that is theta of n square. Matrix multiplication uses n cube. For this we have like this. Then find the binary digits in the binary positive representation. So that will be like this. N is n by 2. It reduces by 2 every time in the iterations. So that will be, answer should be log n to the base 2. Then general plan of analyzing this: upper bound minus lower bound plus 1. Then like this. Mostly it will be like this only. If it is 1, then n. If it is 1, 2, 3, 4 till n, then it will be n into n plus 1 by 2. It will be n into n plus 1 by 2 half n square 1 by 3 n cube. Oh yes, that is why we have got 1 by 2 in this n minus 3 n minus 2 by 2. We have used this formula. Then for 1 square, 2 square and all, we have 1 by 3 n cube. For 1 to n, we have 1 by n square. For 1 power k, 2 power k and all, we have 1 by k plus 1. No, n power k plus 1. And then we have 1 a power I. For this and all, we have a power n plus 1 minus 1 by a minus 1. 2 power I is 2 power n plus 1 minus 1. I 2 power I will be n minus 1 to n power n plus 1 plus 2. These are all the notations you have to learn. And then now we'll find the recursive algorithm. Compute the factorial function f of n equals to n factorial for an arbitrary non-negative integer, that is n factorial equals to 1 to n minus 1 into n minus 1 factorial into n. Then for that is for n greater than or equal to 1. Compute f of n equals to f of n minus 1 into n, that is with the following recursive algorithms. How this recursive algorithm works? We will take it as m of n. Then to compute the f of n minus 1, we use m of n minus 1 plus 1 to multiply the function. We have here as m of n equals to m of n minus 1 plus 1. So substituting them, m of n by n minus 1 in everything. So m of n minus 2 plus 1 plus 1, it will become 2. Then we have this as m of n minus I plus I, which will go till m of n minus n plus n, m of 0 plus n, that will be theta of n. Then the Tower of Hanoi, n discs of different sizes and 3 pegs are there. Move all discs to the third peg. First will be moving m of n minus 1 plus 1 plus m of n minus 1. We mostly use it as 2m of n minus 1 plus 1. Then initially it will be m of 1 equals to 1 here, since there are 2m of n minus 1. So firstly 2m of n minus 1 plus 1, n is taken out as n minus 1. If we want to into 2m of n minus 2 plus 1 plus 1, that will be equal to 2 square m of n minus 2 plus 2 plus 1, that is equal to 2 power 2 square of 2m and minus 3 plus 1 plus 2 plus 1. So in this manner, if we consider, it goes till 2 power I m of n minus I plus 2 power I minus 1 I minus 2 till 2 and 1. So that is equal to 2 power I m n minus I plus 2 power I minus 1. So now to obtain m of n by substituting n equals to n minus I, we have 2 power I by n minus 1. 2 power n minus 1 m of n minus 1 plus 2 power n minus 1 minus 1, that is I equals to n minus 1. We already know that I goes till n minus 1. So that is considered as next 2 power n minus 1 plus 2 power n minus 1 minus 1, 2 power n minus 1, theta of 2 power n. This is the most efficient algorithm for this problem. It is the problem's intrinsic difficulty that makes so computational hard. Exponential algorithm run for an unimaginary long time, even for moderate values of n. Find the number of binary digits in the binary representation. Floor value of n by 2 plus 1. that gives you 0 if n is less than or equal to 1, or 1 plus f of n by 2 log n to the base 2, 1 plus f of n by 2, 1 plus 1 plus f of n by 2, 1 plus 1 plus 1 f of n by 2. That is I plus f of n by 2 power I. That will give you, instead of n, we will write it as I equals to 2 power I equals to n, means I log 2 to the base 2, I log 2 to the base 2, that is log n to the base 2, I equals to log n to the base 2. That is log n to the base 2 theta of log n. General plan of analyzing time efficiency of recursive algorithm. Decide on a parameter indicating an input size. Identify the algorithm's basics operation. Whether the number of times of the basic operation is executed when vary on different inputs of the same size. Worst case, average case, best case must be investigated. Set up a recursive relation with an appropriate initial condition for number of times of the basic operation executed, and then solve the recursive, or at least assertion the order of growth of its solution.
Thank you for watching. Do like, share, and subscribe to my channel.